we have discussed how to carry out basic arithmetic operations, and our focus was to do them in very simple manner without worrying about performance. Today, we are going to see what techniques can be used to speed up the operation, improve the performance. So, in the overall sequence of lecture in this broad topic, as you see that we have discussed the basic design of various operations, and today we are going to talk of speeding up of addition, subtraction as well as multiplication, and finally, then we will move over to floating point operations. So, first what we will do is we will look at a simple adder which we have discussed and see what actually governs the performance, what is the bottleneck. We will see a technique which is called carry look ahead. We will notice that it is carry which is taking time, and some way to compute the carry fast is what is required. Then we will go over to multiplication, and then try to see how multiplication can be carried out in a fast manner. The technique used there would be what is called carry save addition. So, where we postpone use of carry rather than trying to immediately look for carry and wait for it, we will postpone that and add at a different stage. So, in the process we will speed up of the operation. So, coming back to the simple adder circuit which we have discussed, we had discussed how we do addition using paper and pencil, and our attempt was to capture that in a simple circuit exactly the way we do it. That means, we take the corresponding bits of two operands, perform the addition, let the carry go to the next stage. So, this is a circuit which adds two individual bits of the two operands, and these one bit adders are cascaded or chained together to form adder of the right size. So, for example, if you are adding to 32 bit words, then there are 32 units which are put together like this. So, in this you would notice that C 1, which is the carry out of the first unit, is dependent upon C 0, and C 2 is dependent upon C 1, and so on. So, it is this dependence of carry from one stage to other stage which has to be taken into account to complete the operation, and our attention would be focused on this particular aspect of carry going from one end to the other end, from LSB side to the MSB side. What each adder does is a simple task of looking at three inputs, ith bit of A and B, the two operands, and the carry C I as the input, and it tries to define C I plus 1, the carry for the next stage, and S I as a sum for that particular stage. So, it is a simple combinational circuit with two outputs and three inputs. There are different ways in which this can be realized. One possible realization is shown here, in fact, two. S I can be expressed as a sum of product form of expression with the A I, B I, C I as the inputs. Okay. In a more compact form, you can write this as an exclusive OR of A I, B I and C I. C I plus 1 on the other hand is also a simpler form, it is in sum of product form of three terms. So, in this how do you define the performance of such a circuit? So, basically we should go down to how a gate behaves when input changes. So, at some point of time, suppose the input changes, let me suppose we have AND gate, okay, and if you look at waveforms in time, suppose A is 1, okay, and B is 0, up to some point when it changes to 1. Then we expect that C would become 1 in response to this change, but there would be some delay. Okay, C is 0 at when at least one input is 0. So, it is this delay which is attributed to the gate. Okay. So, gate has transistors which switch from one state to other state, and it is that which takes time. So, also the gates are driving some load or some capacitance, and that load has to be charged. So, the charging time of the capacitance is what dictates this delay. So, without going much into details of this delay, we assume that each gate has some inherent delay. Actually, there is also delay in the signals propagating from one point in the circuit to other point in the circuit over the wire. Okay. When you are talking of gates which are extremely fast, where the delays are of the order of picoseconds or tens of picoseconds, then the delays of wires also, the time taken for the signal change to propagate over wire, that also becomes significant and comparable. On the other hand, if the gates were working in nanoseconds or larger, then the wire delays may be negligible. For the present discussion, we will assume that wire delays are not significant, okay, because our focus is on the logic part of the design, and we will take into account the delays which are caused because of the gates. So, now in a larger circuit, when there are number of gates, you have one gate feeding another gate that feeds another gate, then this delay gets accumulated, okay, and the delay would depend upon how many gates you are putting in a series. So, more the gates you have in a series, the larger the delays. So, roughly speaking, you could say that if in ideal condition delay of one gate is, let us say, d units of time, d picoseconds or whatever the unit is, and you chain k gates, then the delay will be k times d. Now, question is this factor d independent or not? Strictly speaking, this d would depend upon how many inputs the gate has and how many other gates this gate is feeding. Okay. So, which means that the delay is a function of fan in as well as fan out, but it is a for example, a 3 input gate would have slightly more delay than 2 input gate, and 4 input gate will have even larger delay, but the delay does not grows proportionally. Okay. It varies, it increases slowly, it does increase, but it increases slowly. So, in a idealized situation, when you are not using gates with very large number of inputs or outputs, then you might assume as an approximate situation that d is more or less a constant. Okay. But we must remember, we must keep this in mind, that we are idealizing, we are making an approximation. Okay. So, as I mentioned, speed of the gate is affected by number of inputs to the gate, and more strongly speed of circuit is affected by the number of gates in the series, and there may be many paths you can trace in a circuit from input to output. The longest path, the path which goes through maximum number of gates in the chain, is called critical path or the deepest level of logic. So, in fact, this is really the motivation why we always try to express circuits, Boolean circuits, as 2 level sum of product, or you can alternatively do product of sum. You can have more complex expression where there is parenthesis and deep nesting of ands and ors, but a sum of product form or product of sum form is most efficient from the point of view of this depth of logic consideration. So, in the current design of the adder which we have talked of, you could imagine that the delay of each 1 bit adder can be brought down to 2 times d. Okay. You can always express that as we did earlier, as we have shown here. We look at this realization of S I and C I plus 1. So, you will have one level of ANDing, you have a series of AND gates and then an OR gate. Okay. I am ignoring again inverters, these complements for the moment. They will also have delay which has to be accounted for, but it will be smaller as compared to AND and OR. So, this circuit can compute the sum and carry in 2D time. So, now if you have 32 of these put together or n of these put together in general, then the delay will be n times 2D. All right. Now, question is how can we reduce this? So, what changes? How do we restructure these gates? How do we reorganize this so that the delay is reduced? So, this is like trying to improve your algorithm, doing same computation in a faster time. So, now as we have seen, the cause of the delay, cause of the large delay is rippling of the carry from one stage to the other stage to the next stage. So, it is because C I plus 1 is generated from C I by this expression. So, that dependence means that C 1 is expressed as a function of C 0, C 2 expressed as a function of C 1 and so on. Now, the question is, can we do some look ahead, can we avoid this ripple? Can C I plus 1 for example, be generated directly from A 0, A 1, A 2, A 3 up to A I and B 0, B 1, B 2 up to B I and C 0. So, of course, C 0 is a primary input which we have to account for, but if we can write for example, can we write C 4 directly in terms of A 0, A 1, A 2 A and A 3 as well as B 0, B 1, B 2, B 3 and C 0. So, we can think of C 4 as a function of these 8 inputs, okay, 4 bits of A, 4 bits of B and 1 carry. So, in principle it is possible, okay, and let us see how we do it. So, let us go step by step. First we write C 1 in terms of A 0, B 0 and C 0, that is the usual expression we have, and we wrote C 1, we wrote C 2 in this form. Okay. Now, all you need is you take expression for C 1 and substitute that in the second one, right. So, and also we expand because we want to ultimately have a 2 level expression. You could have left that in parenthesis, you could say that B 1 plus A 1 within bracket and then expression for C 1 in another bracket, okay, and then you can say that these two are ANDed, but then we are increasing the level of logic. So, our objective here is trying to keep the level low, number of gates which you find in a chain low. So, we expand it and we get a 2 level expression for C 2. Next we take expression for C 3, okay, and take the value of C 2 from this expanded form and substitute it here. You get again a large expression, but still it is possible to get a 2 level expression. One could keep on doing this, okay. You could from this you can generate expression for C 4, then C 5s, and you can go all the way, go up to C 32, and what will happen is that C 32 will have 4 billion terms, okay. So, although theoretically possible, it is an impractical solution, and the assumption we made initially that we will consider that delay of each gate is constant, that is possible only if the number of inputs, number of fan-ins is not very large. But now what is going to happen is that you will have gates with these product terms will become very wide, okay. They will have 32 inputs. So, a 32 input gate will no longer have the same delay as a 2 input, 3 input or 4 input gate, okay. So, although we will keep things 2 level, but our assumption about delay of individual gate will break down. Similarly, there will be large fan out for at least the primary inputs. Okay. You would notice that each of these variable, there are after all 32 A inputs, 32 B inputs, okay, and a C0. All these will be appearing in so many different terms, 4 billion terms. So, there will be a lot of fan out as far as the primary inputs or these AIs and BIs are concerned. So, it is an unworkable circuit. You will be able to verify that this is the number of terms will be of the order of 4 billion, okay, because the first one has 3 terms, second has 7 terms, then you have 15 terms, then there will be 31 and so on. So, it is some power of 2 minus 1. So, you can verify it for yourself. Okay. So, why not we take an approach which is somewhat in between. We do want to have look ahead, we want to directly compute CIs without looking at intermediate carries. So, what we can do is we can basically allow some pre-processing to be done on AI and BI. We look into what role AI and BI are playing in determination of carry and try to do something before we really compute all the CI. So, we have actually 2 stages. In one stage, we will let individual circuits for each bit position digest AI and BI, do something, compute something which is more useful, and then do something what we tried to do in the previous slide. Okay. So, instead of computing CIs directly from A's and B's, we will compute it from some pre-processed form of A and B. So, what we notice here is that the condition under which one particular stage generates a carry and the condition under which it propagates carry. So, when AI and BI both are 1, then irrespective of what is the carry coming from input side, a new carry will be generated. So, we denote this by GI. Okay. So, GI is the condition when carry gets generated in ith position irrespective of what has happened towards its LSB side. Secondly, when any of AI or BI is 1, if the carry is coming from the input side, it will propagate to the output side. Okay. So, CI plus 1 will be 1 if any of these is 1 or sorry, I should say that CI plus 1 will be 1 if CI is 1 and any one of these is 1. So, we denote this expression as PI or the propagate condition. So, now we try to rewrite all the CI values in terms of P's and G's. Okay. So, we can say that C1 is true if either carry gets generated by stage 0 or carry coming in gets propagated at this stage. Okay. Similarly, we can write for C2, C3, C4. So, C2 is P1 C1 plus G1, C3 is P2 C2 plus G2 and so on. Now, in this we can make substitution of the kind we did earlier in terms of A's and B's. So, value of C1 we take from the first line and substitute here, we get another sum of product term. This term we substitute here, we get this, and we substitute here, we get this. Okay. So, again we have growing expression, but you can see that the growth is much more contained. Of course, this gives a feasible way of doing it, but to what extent we can do? We still cannot keep on doing this for 32 stages. So, we will do it for limited stage and then we allow maybe carry to go in the normal way. Actually, coming back to these expressions, we can reason these out directly also. So, for example, here for C2 what we can say is that either carry gets generated at stage 1 or carry gets generated at stage 0 and gets propagated through 1, or there is an incoming carry C 0 which propagates through P 0 and P 1 through stage 0 and 1, and so on. So, similarly, let us look at the last one. The condition for C 4 is that either there is a generation at stage 3 or generation at stage 2 which propagates through 3, or generation at stage 1 which propagates through 2 and 3, or generation at stage 0 which propagates through stage 1, 2 and 3, or an incoming carry which propagates through all these 4 stages. Okay. So, you can either derive these expressions by substitution or reason them out directly based on this logic of what these terms P's and G's are. Okay. So, now this as I mentioned, this can be done to a limited extent. Okay. We will not try to do this for 32 stages, and we will do it for, let us say, 4 stages, okay, which is not very large, and then see what happens. So, first of all, let us understand the circuit which will do this. We have first stage which I have captured in these green boxes. Each one of these contains basically one AND gate and one OR gate. Okay. AND gate generates GIs and OR gate generates PIs. So, we have these P's and G's computed out of A's and B's. Then we have this block which computes all carry values looking at P's and G's. Okay. C 0 is the input, and it will compute C 1, C 2, C 3 and C 4 which has to go out. Then we have the circuits computing the sums out of A's, B's and carries. Okay. So, on the whole there are actually 3 stages, and we can see what is how much the delay this circuit will have. So, can you figure out what is the maximum delay? See, the first stage delay is 1 unit. Okay. There is either one AND gate or OR gate, single level. This second stage has 2 levels. Okay. The third stage also has 2 levels, although I have shown for brevity I have shown exclusive OR, but you can write as sum of product. So, basically there are 1 level plus 2 level plus 2 level, there is a 5 level. In 5D time we can compute all the sums and the final carry. Of course, the carry is coming in 3D time, all the sums are coming in 5D time. So, now we will take this as a module and try to build larger adders. So, first we try to represent this in somewhat abstract form. I have just coalesced 3 stages. Now, we are suppressing internal details, so that we look at the whole thing as a black box and try to put more of these to build larger adders. So, I am just showing that on one side you have A and B inputs, one side you have sums, there is a carry C 0 and carry out C 4, and 3 stages. We are not now separating them out, but there is a box which has 3 stages, and in a smaller form I will show it like that. So, now suppose we connect 4 of these in a chain form, the way we did for ripple carry adder, but now we have units of 4 bit adders, and within 4 bits we have look ahead. Across these blocks of 4 bits we do not have look ahead, we have carry rippling through. So, now there will be, let us see, let us try to find out how much delay this circuit will have. So, remember that the carry comes out in 3D time and sum comes out in 5D time. So, let me write the time when things will come out at different points. So, this comes at 5D, I will omit D, this is coming out in time 3, and from this 3 to this output it will take another 2. So, this just a minute. So, this will take D plus 2D 3. Okay, the carries which are coming out in this will be 3 plus 2 5 and 2. So, this will come out at after 7D, right. You can see that 3 this purple box will take 2D time and another 2D time here. So, 7D, this will come out at 5, 7, 9. So, first let us look at the carry times. So, the time was 0 here, 3 here, 5 here, 7 here, 9 here. Okay. And from this 3 we get 7 here, from this 5 we get 9 here, this 7 we get 11 here. So, the whole thing has taken 11D units of time. If we had allowed normal ripple carry to operate for 16 bits, we would have required 16 into 2, that is 32D. So, there is a considerable saving, and saving will show up more and more as we increase the value of n or number of stages. So, now here there is partial rippling of carry. Question is, can we even avoid that? One way would have been that extend this block or this carry look ahead to 16 stages or 32 stages, but that increases the cost too much and the gates become wider. So, the delay also starts increasing because of that reason. But what we can do is, we can apply the same idea once again at a higher level. Okay. So, we have 2 levels of look ahead. These 4 blocks are as they are, but rather than letting the carry ripple through, I try to do look ahead at that level. That means, try to determine C4 directly from C0, C8 directly from C0 and C12 directly from C0 at the next level. So, what this will require is something which is equivalent to propagate and generate signal at block level. We have blocks of 4 bits, and at each level we generate block propagate and generate signals P0 and G0, P4 and G4 and so on. And this unit which I am showing here, which is looking at these capital P's and G's and generating these carries C4, C8 and C12 and also C16, would be exactly identical to this small purple box which I have shown. Okay. The same idea that C0 is coming here and there are P's and G signals. So, either carries get generated through these G's or carry gets propagated according to P signals. So, now what are these block propagate generate signals or group propagate generate signals? That is what we need to see next. So, we call these group propagate and generate or block propagate and generate signals. So, recall that expression for C1, C2, C3, C4 in terms of P's and G's were these. Okay. So, on the whole, looking at all 4 bits together, we say that this block propagates carry if all small p's are 1. Okay. That means P0, P1, P2, P3, if all of them are 1, then incoming carry will get propagated. Okay. So, we call this as capital P0. This is the propagation condition across 4 stages. G0 is the generation condition in these 4 bits. So, which means that generation takes place either at level 3 or stage 3 or stage 2, stage 1 or stage 0. Generation may take place at any of these 4 stages and propagate out to the extreme left. Okay. So, we say it is G3 or G2 and P3 or G1 and P2 P3 or G0 and P1 P2 P3. So, given this, you can write C4 in terms of capital P0 and C0, that is, this block propagates C0 or this block generates a carry, right. Okay. So, we will have similar conditions for all the blocks and then carries can be computed in this look ahead manner. So, in general we say that Pi is Pi plus 3 and Pi plus 2 and Pi plus 1 and Pi. Gi is again composed of this Gi plus 3 or Gi plus 2 propagating through this stage, Gi plus 1 propagating through these two stages, Gi propagating through these three stages. Okay. And once these are done, we can have C4, C8, C12, C16 expressed in much the same way as we had expressed the carries C1, C2, C3 and C4. So, basically same form of expression, and I will leave it for you to verify. One thing I would like you to notice here about comparison of this form with this form. Here the growth of the number of terms was exponential. Okay. The number of terms is roughly doubling, whereas in this case the growth is linear. Okay. So, that is what has saved us, and why it is linear here and why it is exponential there is because here you have the carry appearing at two places. Okay. So, let us take this. When you take C2 and substitute its value, okay, it gets substituted twice, right. So, that is the reason why it roughly doubles every time, whereas in this case you have only one term containing carry, and when you make substitution it grows by just that amount. So, next time again you substitute once, so it grows by that amount. So, it is growing linearly. And another way of explaining these P's and G's is that the generate term is here, okay, which we have sort of abbreviated as G0, and propagate term is essentially taking this as a common factor. Okay, what is getting multiplied with C0, what is getting ANDed with C0, it is A0 plus B0. So, that is a propagate term. So, once we have taken these out, in the process we have made things slower because we have added more stages, but we have got a circuit which is reasonable and feasible. Okay, now let us move our attention to multiplication. You would recall that I talked about two different types of multiplication. One was when you put number of multipliers, number of adders to add the partial products, and the other one was when we did this iteratively using a single adder. So, let us look at this approach where you have number of adders, right, and we do not have to go through sequentially, because the sequential approach would mean that you have to perform addition, store it somewhere, then redo the addition and so on. So, here also the signals propagate through various adders, but there is no storage involved. So, there is some advantage in terms of speed. So, such multipliers are called array multipliers for natural reasons. What we will try to see is how we can speed up such an array multiplier. Okay, there are many different approaches for multiplication. You can have actually tree multipliers. So, for example, you are basically adding 4 terms, rather than adding them in cascade. What you can do is you add 2 terms separately, 2 terms separately, and then add the 2 sums. Okay. So, when you have to add several terms, you can actually form a tree. So, that is another class of multipliers. We will focus our attention on these so called array multipliers, where you are adding different terms in a cascade form. So, we will look at the question of addition of multiple terms. So, I am not quite showing a multiplier here, but a circuit which adds 4 numbers. Okay. In case of multiplication, these numbers will happen to be those partial products, but let us say we have 4 arbitrary values to be added. You will have one adder which adds 2 terms, next one adds third, next one adds 4th term. So, suppose we put the usual ripple carry adder for each of these stages, then what is the consequence? the signals have to propagate horizontally. There is a carry rippling through, and there is propagation vertical also. You are going from one stage to other stage. Okay. So, the last thing which will get computed is the MSB of the final result. Okay. It has to account for propagation in this direction as well as in that direction. So, here what we can do is since we have to go to the next stage, we have to wait for signals to propagate vertically. We can take advantage of that and prevent propagation of carry to just the left neighbor of one adder cell. So, logically it is equivalent that let us say if this carry instead of going from here to here, suppose it was to be sent to this one, right. This adder has to wait for some of this to come down. Okay. So, meanwhile, the carry of this also can be made available here, and we can also postpone this carry, let it go to next stage and so on. So, what we are doing here is that rather than making carries go to left, we make them go diagonally left and down, and therefore, the additional delay which might come because of leftward carry propagation will be cut down. So, here is a circuit which will do that. So, now you can do this is called carry save addition, because we are saving carry for the next stage. You can do this up to some stage, but the last stage has nothing else to fall back on. So, in the last stage carry has to propagate, okay, and which might give an impression that you would require one extra stage. So, you keep on saving carry for the next stage, and at the last one you add, but what happens is that in the first stage, since you have no previous stage here to feed carries, you can actually have the third operand fed as carries. Okay. So, if you really see, let us go back to this expression of the sum, okay, or even if you look at that, it is symmetrical with respect to A I, B I and C I, right. So, it is only our interpretation that one of these we are calling as carry input, but as far as circuit is concerned, you can think of this as a 3 input and 2 output adder. Okay. It reduces 3 inputs to 2 inputs, and these inputs are interchangeable. So, what we have done is that 3 of the inputs are being added in the first stage itself. Okay. So, from the first stage you have sums coming out as well as carries coming out, both have to go to the next stage, right. So, the next stage is taking these sums and the carries. Carries have to move diagonally, sums have to move vertically, and the fourth input gets added here. Okay. So, AIs have got added here. Well, one could have written A, B and E in the first stage and F at the next stage, but these are all interchangeable, and well, this is showing as plus, this is a resolution problem, this is showing as minus, take it as plus. So, in the last stage we have again sums coming out and the carries. These carries are being added at the sums position, and because we have to have a carry propagation here also. So, you would notice that the number of these adder cells is exactly the same, no more no less, right, but they have been rearranged in such a manner that delays are delays are smaller. Okay. So, how much is, let us compare the delays. In this case, what is the maximum delay? What is the longest path you can think of? You try from any input, try to go to any output. The longest path would be obviously something which leads to this, and there are many ways, because any horizontal movement or any vertical movement, you could either go like that and like that. So, that makes it 1, 2, 3, 4, 5, 6, 7, or if you go like this 1, 2, I am sorry, 1, 2, 3, 4, 5, 6, 7, whichever way you go, there is a chain of 7 adders. Okay. Now, here in the last stage you have one extra, you are noticing one extra adder here, where our numbers were 4 bits, because as you keep on adding, the magnitude keeps on increasing and you have to accommodate for extra bits. So, these carries you do not throw away, let them be absorbed by an adder here. So, there is a delay of 7 units here, whereas in this case again we can try to find what is the longest path. So, you have for example, let us take paths leading to this. We have 1, 2, 3, 4, 5, 6. Okay. There is saving, since we are talking small circuit, it does not show up so much, or we go via other paths. Let us see that nothing is longer than 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So, the other paths are of 5 length, this is the longest path of length 6. One more thing which can be done here in this is that you can replace this with the last stage could be actually a carry look ahead adder. See, carry look ahead adder is more expensive, but faster. We have seen that you have to put extra logic for carry computation. So, we can afford to have one of these adders, that means the last adder as a faster and expensive adder, and then effectively it will be less than 6. Where in this case, if you were to speed up, you will have to speed up each stage to make sense, and it will be much more expensive. Now, let me show you it's this principle applied to 4 by 4 multiplication. Let me switch to let me denote by Pi, Pij rather, Ai and Bj. So, we have to have A's multiplied by Bi's. Okay, well, you can't see that now. Recall that we had A multiplied B equal to sigma of 8 times Bi 2 raised to power I. So, 2 raised to power I is only a matter of weighting it or shifting it, okay, which we will do through wiring. So, Ai, each bit of A will have to be multiplied by each bit of B effectively, and so I am just to simplify things denoting it with Pij. So, we have Pij's for I going from 0 to 3, j going from 0 to 3, and we have to somehow feed these to various adders. So, to this let me feed P 0 0, P 1 0, P20, P30. So, this is A multiplied by B0, the first term, and the second term we need to add is P10, P20, P30, sorry 10, 20, I made a mistake, let me redo it. Okay, P00 actually will stand alone. I will put P10 here, P20 here, P30, then next will be second index will be 1. So, P01 comes here, P11, P21 and P31. So, this is the first stage where I have added A multiplied by B0 and A multiplied by B1. Then in the next stage, I will start adding P02 and so on, P12, P13, sorry P22, 02, 12, 22 and then 32. This can be added here. And in the last stage, we add P03, P13, P23 and P33, and we require 8 result bits. Let me call this S0, S1, S2, S3, S4, S5, S6 and S7, right. These initial carries are 0. So, we have this with normal carry ripple through, okay. And you can see that the delay of this circuit would be again dictated by the paths leading to S7 output, and the longest path would be this. Let me trace it out. Okay. So, for n equal to 4, this delay equal to 1, 2, 3, 4, 5, 6, 7, 8, 8 times delay of one adder, which is 2D. in general you can say that this is you are going to you have propagation horizontally, okay. You have propagation vertical, and you also have some horizontal propagation which is across these stages. So, if you extend this, if you extrapolate this to n, you will have 1, 2, let us see. Okay, actually it will be easiest if you look at this path. Right, okay, which is of same length, but easier to quantify. So, you have some horizontal propagation, some vertical propagation, some horizontal propagation. So, you can calculate exactly, but you would find that it will be something like 3 times n. Okay. This is approximately n, approximately n, approximately n. Right. Now, when we do carry saving, use carry save addition, then what do we get? So, we will require same 12 adder units, okay, and each of these I will look at in this form. Okay, takes 3 inputs, you can put them in any order, generates a sum and a carry. So, P 0 0 I let go straight, okay. P 1 0 and P 0 1 are fed here. I have nothing else to feed here. I could have fed one more here, but there is nothing else to be fed here. So, I will okay, maybe I can leave 1 0 here. Here I can feed P 2 0, P 1 1 and P 0 2. You would notice that what I am feeding along a column, the sum of indices would be same. So, 2 plus 0, 1 plus 1 or 0, 0 plus 2. So, here I will feed P 3 0, P 2 1 and P 1 2. So, I have a need for feeding P 0 3 also at this stage. So, which I can leave here. So, these 4 terms have to be fed in this particular column, and here again I will be left with I will have still 4 terms. So, no, I think I will have 3 only. So, I can take P, let me see, P 0 0, P 1 0, P 2 0, P 3 0. This I have finished. P 1 0, 1 1, 1 2, and I can have P 1 3. Then 0 2, 1 2, 2 2 and 3 2 can go here. Then next one is 0 3 here, 1 3 is already accommodated, 2 3 will come at this stage. And 3 3 will come at this stage. Okay, so I have I added all 1 2 3 4 5 6 7 8 9 10 11. There is something missing. Can you figure out? Zero 3 1 3 2 3 3 3, 0 2 1 2 2 2 and 3 2, 0 1 1 1 2 1. Yeah, 3 1 is missing. I think I should have put that here. Okay, so but there should be, where is P22? All right. So all that one has to do is take care that a term gets added in the right column. Okay, whether it is added earlier or later does not matter. I am a bit doubtful whether something is left out here or not. So you can check. But anyway, this is the overall structure of this adder, this multiplier, and you would notice that the delay now is dictated by this path. Okay. So you have one diagonal movement and one horizontal movement. So roughly it will be proportional to 2n instead of 3n. So let me just conclude. So what we have seen is that as far as addition is concerned, and same would be true for subtraction, the key idea was to go from ripple carry to carry look ahead, and go from O n type of delay to O of log n type of delay. Why we get log n is because when you do multiple levels of look ahead, suppose we went from 4 to 16, okay, we got 2 levels. If suppose we were to go to 64 bit addition, right. So we had one unit looking across 4, another unit at the next level will look across 16, and then yet another level will look across 64. So it grows like a tree, and the number of such look ahead levels will be given by, it will be proportional to log n. So I am not putting a base here. If you have individually look at across 4, so it will be log n to the base 4, but that is only a proportional factor. Whereas in case of multiplier, we moved from delay which is proportional to 3n to delay which is proportional to 2n by doing carry save addition. So there is a sort of 3:2 roughly, which is the saving. I will stop at that.